Hello, seekers. Welcome to the sixth video of the blockchain series. In the previous video, we spoke about, or in the previous video, we phrased this mathematical problem of and introduced this variable called Wi on a blockchain which has a rolling window for 5 years. Five doesn't matter, but it's a rolling window, right? And the blockchain had I and Z blocks, and we introduced a variable of Wi, which was the probability that a dishonest node succeeds in building a blockchain of length I plus Z plus 1. That becomes the longest chain when it attempts to tamper with a transaction in the ith block, right? And if this probability is significant, then the entire blockchain network is not secure, because a dishonest node will be able to build the longest chain, and which means that will be considered as a truth by the rest, right? And if the probability is low, then it means that the honest nodes are building the longer chain, and this will never be able to convince the other nodes in the network as the truth, right? We also introduced this variable of n, which is nothing but the length of the longest chain, which is I plus Z plus 1. And we also saw how W0 is 0 and Wn is 1, right? Now, in this video, we will derive the formula for, we'll derive the value for Wi, right? Now, before we start, think about what can happen. A node, a dishonest node, when it decides to tamper with a transaction in the ith block, right? So let's say there are Z blocks and it's a rolling window. When a dishonest node tries to tamper with a transaction here, what is likely going to happen? So the dishonest node is trying to do that in pursuit of changing this, rebuilding this block, and building all the subsequent blocks and coming here, right? Building one additional node here. And it is trying to do all that while the honest nodes are also trying to build that next block, right? So in a way, the dishonest node has a bit more work to do because it has already broadcasted the transactions, and it is trying to come back and redo that by building an additional block. So when a dishonest node is trying to do this, if the dishonest node is faster than the honest block, it means that it will come closer to Z, right? Because if you consider this whole thing as a rolling window, right? This is a rolling window. When a dishonest node is able to build this sooner, it means that it will come closer to Z as the next step, or it can fall back one step even behind. It can go back here in that rolling window, right? If the honest nodes are faster, right? These are the two possibilities. When I'm Z nodes deep, when a dishonest node is Z nodes deep, and if I'm not fast, it means that I will go one step below. But if I'm faster than the honest nodes, it means that I will go one step ahead, closer to Z, right? And which means that if I were to rephrase Wi, and there are two possibilities. Either I can go to Wi plus 1, or I can go to Wi minus 1, right? Now, what this means is that the probability that that I can succeed from the ith node is actually the sum of the probabilities that I can succeed from the I plus 1th node or the I minus 1th node, right? These are the two possibilities for me to when I succeed in when I either succeed or fail in building this particular block. If I succeed building this block sooner, it means that I come here. If I don't succeed here, it means that I go back one step behind, right? So I can express this, the probability that I can succeed from I, as the probability that I can succeed from I plus 1, and the probability that I can succeed from I minus 1, right? Because these are two possibilities for me from here before I reach Z. Now, Wi plus 1, again, what is this again, right? What is the probability that I can reach here versus what is the probability that I can reach I minus 1? It all depends on the compute power of that dishonest node, right? If the compute power of that dishonest node is, let's introduce the two variables here. P is the fraction of the compute. If P is the fraction of the compute managed by honest nodes or controlled by honest nodes, and Q is the fraction of compute controlled dishonest nodes. Right? Now, if this is the fraction, say let's say if there are 10 CPUs and if dishonest nodes have control 3 CPUs, then the fraction is 0.3 for this, then Q is 0.3 and P is 0.7, right? So the probability, right, from WI, if I'm expressing that as, WI plus 1 and WI minus 1, which means that the chance that I might get into WI minus 1 can happen when which means that I'm actually falling back. The dishonest node is falling back, which means that the honest nodes control. I mean, the honest nodes are faster, right? So, which means that the probability that the honest nodes would succeed would push me back, right? And similarly, the probability or the fraction of the compute that is controlled by me is going to push me forward, right? So the factor of Q is going to push me forward. The factor of P is going to push me behind from the standpoint of a dishonest node. So WI can be expressed as this. A combination of the probability of succeeding from I minus 1 and I get to I minus 1 and because of the fraction, because of the compute that is controlled by the honest nodes, and I get to the I plus 1 through the compute that is controlled by the dishonest nodes, right? And we know that the total is equal to 1, right? P plus Q is equal to 1 because out of the finite compute resources, if Q is a fraction for dishonest, then it is 1 minus Q for the fraction of the honest nodes. So P plus Q is equal to 1 here, right? Now let's derive this value. Let's expand this and see where this takes us. So let's start clean here. Let's restate this value of WI, which is equal to let's rearrange this. Let's start with P times WI minus 1 plus Q times WI plus 1. Right? So yeah. So now we know that P plus Q is equal to 1, and so we can simply multiply WI with P plus Q because it wouldn't change. So P plus Q times WI is equal to P times WI minus 1 plus Q times WI plus 1. Now let's rearrange this. Let's rearrange this whole equation. Let's talk about let's say Q of WI plus 1 minus Q of WI is equal to P of WI minus P of WI minus 1. Right? I've just brought in, I've just rearranged these here, which means that your Q times WI plus 1 minus WI is equal to P times WI minus WI minus 1. So which means that WI plus 1 minus WI is equal to P by Q of WI minus WI minus 1, right? So we have brought in here, right? So this is let's keep this for now. So this is a general equation, right? So Wi plus 1 minus Wi is equal to P by Q of Wi minus Wi minus 1. Now let's try to expand this a bit. If you are very specific, let's talk about, if you consider for when we consider I is equal to 1, how will we when I is equal to 1, the same equation can be written as W2 minus W1 is equal to P by Q of W1 minus W0, right? When I is equal to 1, and which is nothing but we know that W0 we know that W0 is equal to 0, right? So which means that which is equal to P by Q of W1, right? Now when I is equal to 2, the same thing can be written as W3 minus W2, which is equal to P by Q of W2 minus W1, right? And you can write it and you can keep writing this right, for different values of I. So can we generalize the above? Yes, we can try to generalize that. We can generalize the above as Wi plus 1 minus Wi is equal to P by Q to the power of I times W1. How did you arrive at W1 here? So if you notice here, when I is equal to 2, we can actually replace this as P by Q times W2 is nothing but from here that W2 is nothing but W1 plus P by Q times W1. So you can take it as W1 plus P by Q of W1 minus W1 here, right? So if you take here this way, then you know that these two cancel out, and this becomes P by Q times square of W1. So that is how we are arriving at this pattern. So when you're generalizing this for all values of I, it is, you can restate the equation as Wi plus 1 minus Wi is equal to P by Q times I times W1, right? So let's keep this as well. Now now you can also state this. So from this, let's consider Wi plus 1 minus W1. What would that value be? Wi plus 1 minus W1, right? What would that be? Wi plus 1 minus W1 is equal to Wi plus 1 minus Wi, right, plus Wi minus Wi minus 1, so on till W2 minus W1, right? We can restate it like this: Wi plus 1 Wi plus 1 minus W1, right? This is actually Wi plus 1 Wi plus 1 minus W1 can be restated as this: Wi plus 1 minus Wi plus so and so. And all the Wi's will get cancelled here, Wi minus 1 will get cancelled here, and you can restate it, right? Now we know what this is, right? Wi plus 1 minus Wi is so and so, right? Now, which means that this is nothing but, you can replace, you can state this as a sum of, where k goes from 1 to I, of W k plus 1 minus W k, right? That is how you can generalize this. This is an entire sum. And this is nothing but which is equal to W1 times k is equal to 0 to I times P by Q times k, right? So yeah. So sorry, so this is not 0, so this is still 1. So this is still k is equal to 1 times p by q of k. Now, which means that wi plus 1 minus w1 is equal to w1 times the summation of k is equal to 1 to I times p by q times k. So which means that wi plus 1 is equal to you can add this one, you can bring w1 on the other side, which means that it can be simplified as between k is equal to 0 to I times p by q times k times w1, right? So you can replace it. You can arrive at this value, right? I mean, if you were to split this, it's nothing but if you want to do it in 2 steps, you can find that wi plus 1 is equal to w1 plus w1 times k is equal to 1 to I times p over q times k, and and this would lead you to this value, right? So we have arrived at this value, and this is a geometric series. Now the value for this is the derivation of this one. The specific point is outside the scope of this video, but if you do a quick research, you will see that this is a geometric series, and this equates to which means that this can be rewritten as wi plus 1 can be rewritten as w1 times 1 minus p by q times I plus 1 divided by 1 minus p by q. So we have basically expanded this part. We have expanded this part into into this. So this part is expanded into this one. Now, this is so far we've gotten till w I plus 1. So we know that if you move forward with this, we already know that let's see. We know that wn is equal to 1, right? We saw that some time back. Wn is nothing but 1, right? So we saw that. Now, what if we were to equate it in this form? So wn is equal to 1, which is also equal to w1 times 1 minus p by q times n divided by 1 minus p by q, right? So this is what is this is how we can rewrite for wn, which is 1, and you can rewrite it in this formula too. So from this you can pretty much calculate w1. So this leads you to w1, which is equal to 1 minus p by q divided by 1 minus p by q to the power of n, right? So this is w1, right? We have actually derived the value for w1 here. Now, when you put this, this w1 into this value, right? When you put w1 into this value for wi plus 1, what do we get? So we will get wi plus 1 is equal to 1 minus if you replace w1 into this equation, what do we get? We get this whole thing of 1 minus p by q over 1 minus p by q to the power of n times this whole thing, right? Which is 1 minus p by q to the power of I plus 1 over 1 minus p by q, right? So this is what you'll get. Wi plus 1 is this, and here you can find that these two can cancel out, and this becomes equal to 1 minus p by q to the power of I plus 1 over 1 minus p by q to the power of n, right? So this is how we have derived I plus 1 here. So from Wi plus 1, we can actually write the value for Wi, which is going to be Wi is going to be equal to 1 minus p by q to the power of I divided by 1 minus p by q to the power of n. So this is what we wanted to derive earlier, right? And we know that n is equal to I plus z plus 1, right? So if you recall the original thing, we captured n to be equal to I plus z plus 1. So which means that you can restate this whole thing as Wi is equal to 1 minus p by q to the power of I divided by 1 minus p by q to the power of I plus z plus 1. This is the value for Wi. So this is the probability. This is the probability that a node, a dishonest node that is trying to tamper with a transaction that is z nodes deep. To come back to our earlier example, so this is the probability that a dishonest node that is z nodes deep, that is, it is trying to tamper with the block here in I. The probability that it can actually succeed is what we just derived, right? Which is going to be 1 minus p by q over 1 minus p by q over I plus z plus 1. We can refine this further. We can take this a bit more steeper. We can push it further. See, we have taken this example considering a rolling blockchain, right? We took a blockchain of n number of blocks, right? If you see here, our blockchain was sorry, it's not n. The blockchain was I plus z. And what if this node keeps trying? It never gives up. Say the first time this node starts with the z nodes deep, it tries to build it, but it is overtaken by the honest nodes, which means that it goes I minus 1. But it keeps trying. It means that if this node has to, what would happen if this node, the dishonest node, never gives up? If the dishonest node keeps building this block, how many ever times it fails, it means that it can go fall beyond to an extent that it can go so deep into the blockchain, right? And which means that what if you consider this? What if you relax this whole rolling window and consider this as an infinite blockchain? In other words, what would be this value when I tends to infinity? So when I tends to infinity, limit when I tends to infinity, what would be the value of Wi? Now, this is nothing but when the value of I goes to infinity, and when we try to capture the value of Wi, means that that specific dishonest node never gives up. It never comes out of the blockchain because it's not a rolling window anymore. So it means that it keeps trying for eternity, right? Now let's calculate that value, right? That is the extreme case of a dishonest node, that continues to keep trying. And for that, we will try to put that value of we'll try to calculate the Wi as I tends to infinity. Now, just before this, let's expand this a bit before we calculate this value. So Wi can actually be written as, right? So this whole thing can be written as this one, the numerator part. This one, you can basically write it as P by Q times I times P by Q times minus I minus 1. I have just rewritten the numerator this way, divided by, if I'm going to take the same thing here, P by Q times I, even in the numerator, which is going to be P by Q times minus I minus P by Q times Z plus 1, right? Now this is going to be equal to, I can now cancel these two with each other, which is going to be equal to P by Q times minus I minus 1 divided by P by Q times minus I, minus I minus P by Q to the power of Z plus 1. Okay, so this is the value. Now we can further rewrite this as Q by P times I minus 1 divided by Q by P times I minus P by Q times Z plus 1, right? Yeah. So what would happen when the value of I turns to, when I goes to infinity? When I goes to infinity, it means that the dishonest node never gives up. And in a situation where the honest nodes control most of the network, what would this value be? Which in a way that, let me take this off. In a way, when Q is going to be less than P, what would the value of this be? Wi, right? When the honest nodes are the majority, form the majority, and in that scenario, if the dishonest node never gives up, which means that I tends to infinity, what is the value of Wi? Now you can notice that when I tends to infinity, this value is going to be Q by P is going to be less than 1, right? Because Q is less than P. So Q by P is going to be less than 1, which means that when I tends to infinity, this becomes a negligible value very close to 0. Same is the case here. So these two parts will become 0. So this becomes equal to 1 over P by Q times Z plus 1. Or it can also be written as Q by P times Z plus 1. Right? So we have reached the value of your limit of when I tends to infinity, that is when the dishonest node never gives up. The probability that the node will still succeed, which is Wi, is going to be given as Q by P times Z plus 1. So this is your final formula here. Now if you really see this value, your Z is the number of the nodes that the blockchain is deep in, right? And we have taken that, in a network where the honest nodes control most of the compute power, which means that Q is less than P. Now this value by itself becomes less than 1, right? Q by P becomes less than 1. So if you just consider the value of z, as the value of z increases, z is nothing but how many blocks is that that the dishonest node is trying to tamper in, right? So as z increases, we see that this value completely shrinks. It goes smaller, right? And it becomes negligible. The moment z becomes, even when greater than 2 or 3, this value becomes even so negligible that, it is the probability that a blockchain is going to, probability that a dishonest node is going to succeed becomes negligible, becomes close to zero, right? You can try that out with values of values of v as if you consider, q to be equal to zero point 0.2 and p to be equal to 0.8, right? Which means that, your dishonest nodes control 20%, which itself is a fairly high number. So in that case, your q by p becomes 1 by 4, right? And which is nothing but 0.25. And 0.25 times, if you really find the value of 0.25 times, so this is your q by p. So q by p, when z is equal to 1, your value becomes 0.25 whole square, right? When z is equal to 2, it becomes 0.25 whole cube. When z is equal to 3, it becomes 0.25 whole power 4. Now you see that these values decrease exponentially, right? As z goes from 1 to 3, these values will drop exponentially, which means that as long as the more a dishonest node tries to go deep into that network to do some tampering, the probability that it is going to succeed building the longest chain drops drastically. So that's the point that this makes, right? As z increases, the probability significantly drops for that dishonest node to catch up, as long as the network is the majority of the network is managed by honest nodes. So this completes the first part of the proof. So what we have seen here is, the probability that a dishonest node going back in time and correcting that, and then coming back and building the longest chain. So that probability is completely negligible. That's what we have seen here. But what if a dishonest node does that immediately? It doesn't go back in time, but it makes a transaction with another party, immediately comes in and changes it. What is the repercussion of that is what we are going to see in the second part of the proof. Thank you.
If you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.